All right, so today we're going to talk about something called Euler's method. So Euler is how you say that, ain't Euler, named after the famous mathematician Leonard Euler. There might be an H in there somewhere. He's German. Euler came up with a lot of amazing things. You know how we use the letter E all the time? Guess what it stands for? Euler. He came up with that. And he also came up with the very famous formula, e to the pi I equals -1. So sometimes equals 1, equals positive 1. Some people like to write e to the pi I minus 1 equals 0. We're actually going to learn in this course later in about April-ish why this is true. We're going to learn that. Anyway, Euler, he got his name on this method. He might not have actually done it or had anything to do with it. Some people just get their names on stuff. And Euler's a guy who did so much stuff that his name is unlike everything. Anyway, so here's what we're looking at. We have a differential equation, dy dx equals -2x over y. And I'm giving you a particular condition, 0, 2. Now, you could actually solve this differential equation because it's separable. So what Euler's method is about is, what if it weren't? What if instead of -2x divided by y, it was -2x plus y? Then the equation would not be separable and you would not be able to solve it easily. In fact, there are many, many equations which cannot be solved by any analytic method at all. Therefore, we have this approximating method called Euler's method, and there also are much more sophisticated versions of the same thing that take into account more derivatives and so forth, and you'll learn about those if you take differential equations at university. So here's how it works. As you start at your particular condition, this particular condition is properly an initial condition since it's at x equals 0, but we're going to see maybe this isn't necessarily a time-dependent function, so I like particular conditions still. And so what we're going to do is we're going to say, all right, let's call this point x0, y0, and we're going to start there. So we're going to start at 0, 2. And we're just going to see, in this example, we're just going to see how much of the solution can we construct. All right, so here's the basic idea. I have a point x0, y0. Let's just label it x0, y0, okay? Now, because I have an equation for dy dx, I don't have an equation for the function I'm looking for, but I have an equation for dy dx. So what I can do is, I know what the slope is at this exact point. In fact, that slope is dy dx evaluated at x0, y0. All right, and what we're going to use is that if I were to move over from my x0 a short distance delta x, like we always like to do in calculus, all right, then what would the delta y be? Well, dy dx at this point is approximately equal to delta y over delta x, where delta x is some number. You know, we're going to use often something like 0.2 or 0.1. All your homework uses 0.2 or 0.1. You're going to see that this is a method that really lends itself to computers and mathematical computing. All right, so well, since this is the case, that the slope is approximately equal to delta y over delta x, that means that the delta y is approximately equal to dy dx evaluated at x0, y0 times delta x. And that's how I can know what the delta y is. So I can basically, like, I know what my delta x is, I know the dy dx at that particular point, and so the approximately equal means I'm going to follow a straight line. Use a linear approximation, essentially. And then, so what I've got here is a distance. I made it go down, as though the dy dx were negative, which it might be, it might not be. So this is our delta y, and delta y is equal to dy dx, x0, y0, delta x. Yeah, and then the point that we get that way, all right, that's our next point, which we're going to call x1, y1. And so we can say things like about the x1, y1, well, since I moved over delta x from the x0, x1 is equal to x0 plus delta x. And since I changed the value delta y from my y0, y1 is equal to y0 plus delta y. I say plus even though my function went down here, because delta y was negative, all right, in this example that I just made up. All right, so that means that my point x1, y1 is in fact equal to x0 plus delta x, y0 plus delta y. All right, now we've got everything that we need here to set up what is called Euler's method with a delta x equals 0.2. And that's probably what we're going to start doing next. And so I'll start that in our next video, how to start using our fundamental equations that we're going to use. I mean, I guess we're going to take this one, we're going to simplify it a little bit. We're going to take this one. That's going to be one of our key equations, and we're going to simplify it. We're going to understand that the x0, y0 is implicit. So we're going to say delta y equals, we're going to dispense with the approximately equal, dy dx delta x. We're just dispensing with the approximately equal to, because we understand that the delta y isn't the real delta y of the function itself. So one of the things to be aware of is why this method is approximate. It's not exact, because I knew the slope just at this point. Well, between here, this point and this point, that slope could have been changing as it went along, right? Because I could have a whole slope field in here of different things. That if I zoom in really tight, the slope field, hopefully it doesn't change this much, but that slope field could change in there. It doesn't have to stay at whatever value is here, so that by the time we get down here, our slopes have changed a lot. Now, the other thing that we're going to understand is that our x1 and we could do this repeatedly. So once I get this point, I could then do the process again, get another point. So in general, I can say that I have an x sub n plus 1, which is equal to x sub n plus delta x, and a y sub n plus 1, which is equal to y sub n plus delta y. And delta y is going to be found from this formula right here. All right, so these really are the engine of Euler's method that we will use. We'll set up a nice table, and we'll see what the pros and cons are of this method for solving differential equations.